Okay, so now we're going to do a bit more with that normal curve. Remember, this is the normal curve, and it's more of a hill than it is a line. So all the values inside, there's a whole bunch of data members that's pushing this up, almost like a histogram kind of thing. Okay, so the area under the normal curve is 1, and it represents 100% of the data. So when we deal with this, we deal with probability and percent. And they're related, as you can see. One's 1. That would be the probability that value falls in the normal curve, and 100%. Okay, so we're just going to go through and do the difference between, we're going to find the probability, we're going to find the percent, and it's just literally multiplying things by 100 to get there. Okay, z-scores are literally the measure of how many standard deviations the data is from the mean. And as you know from yesterday and previous work, if you are 1 standard deviation above the mean, if you're 1 z-score, I guess, you're 1 standard deviation above the mean, 2 standard deviations, 3, and then if you're backwards, you're negative. So 1, 2, and 3, so this is positive z-scores. Below the mean is negative z-scores. Instead of dealing with just z-score of 1, we're going to deal with the z-score of 1.25 or 1.386, So it's not just these nice 1, 2, 3 z-scores. We're going to be dealing with z-scores in minutia, I guess. So this is the formula. It's basically just taking the difference of the mean, obviously because that's the distance from the mean, and then dividing it by the standard deviation so we can figure out how many standard deviations away you are. Okay, so for example, a college entrance exam is designed that the scores are normally distributed between 500, with a mean of 500 and a standard deviation of 100. So we know we put the 500 here, we could put 600, 700, 800, and 400, 300, 200. In essence, okay? So if we want a z-score of 700, that's right at the 2. So it has a z-score of 2. We could do the whole formula with it, which would be the data value minus the mean divided by 100, which of course will be 2. So if you can figure it out just by looking, so 400 is negative 1, power to you. Okay? Most of the time, however, you may not be able to. We want a z-score for 249. Now that doesn't fall in any one of these whole z-scores or whole standard deviations. So using the formula is kind of necessary. So this is below the mean. 249 is lower than 500, so this is going to be negative. So 249 minus 500 divided by 100 is negative 2.51. So it's about right here. That's where that is. So it's pretty low. And it's pretty far below the mean. Okay, here's 734. Again, that one's tough to do, just eyeballing. Okay, so we use our data value minus the mean divided by 100. We get 2.34. Okay, which makes sense. It's more than 700, so it should be higher than 700. So in 700 had a 2 z-score. Okay. Sorry. So now we're going to be using those things to compare. So 2 different sets of data, you take a test, someone else takes a test, they say they did better than you, but if they're different tests, how can you really tell? So that's what this is all about. A set of math exam scores, so you have a math exam and you have an English exam. Now you could just go by score alone, but that's really not going to tell you much, especially if one was an easier test than the other. Math is always easy, so there you go. No, I'm kidding. So a math exam score has a mean of 700 and a standard deviation of 8. Okay, so math score has a mean of standard of 70, standard deviation of 8. Okay, and then the English exam has a mean of 74 and a standard deviation of 16. I'm just boxing one in and circling one so I can tell the difference because they both have the same pieces. And they want to know 78. If I got a 78 on both of those, which one did I do better on? Okay, so the first one's pretty easy. The math score, if I have a mean of 78, you can see just by your foray into the standard deviation that one has standard deviation of 1. For English, you want to know what you did with the 78. So 78 minus the mean divided by the standard deviation is 0.25. Or 1/4, however you want to do it. Okay, so which one did you do better on? The one where you have a more positive, a higher standard deviation. So a higher standing means higher z-score. That's it. And you know that from the normal curve. If the mean is here, if you got one standard deviation, you're here. And if 0.25 would have been right there. So you can tell you're higher, you're farther up. Okay, number 2. Okay, we have a IQ tests. Now Mensa takes IQ, but they also take SAT scores. So if you want to know who's smarter, I guess. So we have, let's see, if we read this over, assume that the mean combined SAT score is 1,500. I'm going to just underline this, with a standard deviation of 300. Michelle took the SATs and got a 2070. So we have an SAT score for Michelle. Okay, and then we're going to have Eileen took an IQ test and scored 129, where the mean is 100 and the standard deviation is 15. So with Eileen, she took an IQ test. So we're going to see who's smarter. You can't really tell from this, but we're going to tell by who did higher in the standard deviation. Okay, so what we do is we figure out the z-score for Michelle. So she got a 2070. The SAT's mean was 1,500, excuse me. We divide that by 300. When we do that, we get approximately 1.9. Okay. Now rounding is up to you. You'd have to see the results to see which one's best. But you're just comparing, so we're not going to tell you where to round to when you're just comparing two scores. So, and this one is 1.93 repeating. So when you do something like this, which one is higher? Well, this one is higher. So Eileen is slightly more intelligent. Okay. Next, last one we have two versions of a standardized test. And in April and in May. So we have two of these. The April version shows a mean of 480 and a standard deviation of 24. The May version, 510 and 220. Assume the scores are normally distributed. So we say Joanne took the April test. So she's April. That's my underline. So Joanne took April. So her z-score or standard deviation above the mean would be 510 minus 480 divided by 24, and she would have a 1.25 standard deviation or z-score. What would Steve have to say he did as well as Joanne, or did the same as Joanne? So we're not asking for his z-score. We're asking, well, what grade would he have to get to have the same z-score as her? Okay, so basically what that's saying is, since Steve took May, we want to know, he already knows that he wants to get a 1.25 standard deviation, but we don't know what his test value is, or his value. So we're kind of using the formula in a backwards way, okay, where we're not just plugging it in and getting an answer out. Okay, and the easiest route to do, just do a little cross multiplying, and you get 25 equals x minus 510. Okay, and he should have to get 535 to get the same score, or in another way to say it, the relative same score, the same standard deviation, the same z-score, that's what he would have to get. Okay, in order to say that he did as well as Joanne. All right, have a great day. What just happened?